Well, let's see. Welcome everybody. This is part of the beginners talks. Let's see, on graph databases and Networkx. So, first of all, how many of you have used graph data? Oh, okay. All right. How many of you have used graph databases before? A couple of you. How many of you use them for home? For work? Let's see. For school. Okay. Wow. All right. Let's see. Same one person. Let's see. Did you use Networkx specifically? Okay. Let's see. First of all, I'm going to be working for Continuum, so I need to let you know. Download Anaconda, and you can be able to do any of the anything that you see up here with IPython Notebook or Networkx. It's included. So, new version just came out this week. So, Networkx is a library that creates and works with graph databases. And so here's what I'm going to be covering in the talk. What graph databases are, and basic tasks involving nodes and edges, how you can use algorithms and examples of moving your domain problems to Networkx, and saving your graphs for later for use in other applications. Let's see. According to our keynote speaker, this is an awesome project. Let's take a look at the Networkx homepage. Let's see, Networkx is a Python language software package for the creation and manipulation of study of structure, dynamics, and function of complex networks. We're going to find out what that means. We're going to be going through data structures using graphs, digraphs, and multigraphs. We're going to take a look at many standard graph algorithms, network structure and analysis measures. We're going to take a look at some of the generators that Networkx provides. And let's see, you can be able to get to the documentation very easily. So according to our keynote speaker, this is a pretty awesome topic. So let's go ahead and get started. These are some, simple, this is a simple graph. Here's some ways that you can add nodes. Let's see, the first thing, we import Networkx as NX. This is just a convention. If you're just working with one graph, you can call it by simple names. Otherwise, this is a horrible variable name. Let's see, NX graph, or NX.graph. This will allow you to create nodes and edges. Here's how to create nodes. It's, adding one node is as simple as just saying, or this function add node. You can add nodes of different types, strings, anything that's hashable. So you can also add, nodes from a generator or any kind of iterable. You remove nodes just as easily. You can draw them using a default render. This uses matplotlib. So far we've got, 5 nodes. If this was Facebook, you'd have 5 people. And here's how you can add the edges between those people from one node to another. So far, nodes 5 and 6 got, might not exist because they were removed. So if you try and add in an edge that they don't exist, well, now they will. So it'll create the edge, it'll create the nodes. This is a simple way to add a whole bunch of edges at once. You can have cyclic edges. An edge that cycles from one node to another, one node to the same node. But you might not see it, that cyclic node in your graph. So you will need to query for that one specifically. Removing edges is just as simple. So you can remove an edge from 5 to 6. You can remove lists of tuples. You can give it edge lists. And finally, getting rid of all the edges. Networkx is written in pure Python. So what about speed? Let's see, if you wanted to create 1 million nodes, we'll give it some time here, find out how long it takes. let's say you want to move a little less than 5.5 seconds. Let's see. Let's see. There are several. You don't have to use your own data to try this out. You can use already existing graphs. These algorithms for creating these graphs are already in here, so are already in Networkx. If you go make a complete graph, a complete graph is just all nodes are connected to all other nodes. So this one's 4. You can make much more. There are several others that are listed in here. This is the Southern Women graph. The Davis Southern Women graph is one of those things you have to study if you're doing social network analysis. So I'm obligated to put it in here. I'll say the difference is this is a bipartite graph. There are 2 sections. Each one of these nodes is either a club or a person. So it just shows the connection of these Davis Southern Women to the clubs that they were in. Here's some other examples. The Karate Club graph shows a split of 2 karate clubs and the people and the way that they split themselves up. Now, these are all numbers. You can't really tell that these are bipartite until you take a look at the data. So you can say data equals true if you want to get the nodes. And you have the Mr. High Club and the Officer Club showing up in the data. It shows up as a dictionary. Each one of these nodes can contain a dictionary. Each one of the edges can also contain a dictionary. So let's see. Be careful about having too many nodes in a graph. This is an Erdu-Shreni graph. It's 250 nodes with a random, let's say, 10% distribution of edges. Now, if you do have a large number of nodes and you can't plot it out with the default render, there are other renders in Networkx. You can take these graphs and take it into other applications. We'll be taking a look at one later to kind of tease these nodes apart. So if you do a large graph like this, you might only get anywhere from 1 to 5 nodes that are interesting. Node 11 seems to be pointed out. I guess I should talk about the default render. The default render is a spring graph. What it's trying to represent is a series of nodes and springs. If you threw up this conglomeration of nodes and springs into the air, bounce around and you take a snapshot picture, let's say, this is something that you might get if you had too many nodes and springs. Let's see. The second type of graph that we're going to be talking about is called a directed graph, which has directed edges. Let's say the person in the center here is a movie star. Lots of people on Twitter following him. He doesn't necessarily have to follow the people back. So this is more like the Twitter graph rather than Facebook. Let's see. In social network analysis, each one of these people might have a degree. Let's say this person down here at the bottom, number 4, has an out degree of 1. There's one node pointing out. He's got an in degree of 0. The person in the center has an in degree of 9. There's 9 other people pointing to him. And if this didn't have any kind of direction on it, if it wasn't a directed graph, it would just have a degree. Person 0 would have a degree of 9. Sometimes these can be highly clustered, so cliques. There might exist cliques inside this big old mass. Let's see, groups of highly connected components. And the small world problem is going to be how distant something is from, or one node is from another. So let's see, you've heard of the 7 degrees of Kevin Bacon. So that's part of the small world problem. I think Facebook has got it down to like 4.5. An average distance between people is 4.5. All right. So this is another example. We can create these directed graphs. These directed graphs are directed in the exact opposite way you would think. Let's see. the bold lines at the end might as well be arrows. So we're actually pointing from 0 to number 1, 2, and 3, opposite of the arrows. Anyway, so you can create these from generators. If the nodes get too unwieldy, you can nail them down with a position argument. So if you've got something like this, you can specify the positions for each one of these nodes, but the positions have, let's say, you have to specify all the positions. You can't just specify some of them. And that's done with a position argument to draw. So what I've done is I've created some paths because I was being lazy with how many edges I wanted to create. And let's see, the position argument shows which node you're affecting and the XY values in the tuple. So you can nail it down and get the same render every time. So usually the renders, let's say, it is that ball and spring system, and so you're not guaranteed to get the same type of rendering every time. A multigraph is let's see, able to add several edges between nodes. So here I have add edge between 1 and 2 twice. I'm just letting you know you're not going to be able to see it in your renders. But if you did a query for it, we'll be able to see that in just a minute. This is a multiple directed graph. It's the same as a regular directed graph, but it can have multiple edges. I've got multiple edges between 2 and 1 here. You might be able to see arrows at both sides of the connection. And if I asked for how many edges, it would come back with the list of all of the edges, not just the ones that you would see in this graph. Each one of these nodes and each one of the edges contain data. So it's a dictionary. If you're used to working with relational databases, you can think of these as the primary key of a tuple in the ID field. That's not the only way to think of these things. Inside these nodes, I can add a graph. So we can have a graph inside the data of a graph, or we can have a graph as the node itself. Let's see, because NX graphs have a property that they're hashable. From here, I'm adding some information. I'm adding a path to that one node because there is a graph inside that node. You can place data in it, or place data inside the graph. So the reason I bring this out is because you can't do this, well, let's see, well, I'm sure it's possible to do it with a relational database, but I wouldn't try past too many levels because you'd have to have a database inside a tuple inside your database. So it doesn't work after a while. So if I wanted to print that out, nodes data equal true, I could print out, this is a printout of the data of the graph inside a graph. Let's see, the nodes and edges can be of any hashable data type. So it can be, let's see, strings, tuples, numbers, let's see, and a couple of others that I'll get to in a minute. Let's see. This one's pulled from the Python Challenge website. We're going to get into how do you migrate your domain into Networkx. So this was the challenge. Let's see. To solve this maze, these are 1 pixel by 1 pixel, let's say, mazes, 640 by 640. Let's see. So all I'm doing is converting it to a black and white image, which I'm not ruining it for you if you want to go through the Python challenge, but let's see. We're going to solve this in about 5 minutes. Let's see. I'm going to just quickly run through these. I'm going to open up the maze, convert it to RGB, I don't have to, but let's see. I'm going to need to turn some of the pixels blue. I'm going to define some colored pixels so I don't have to keep thinking or typing tuples. Since the pixel values are tuples, we can use that for the node name. So I'm going to use, all right, let's see, I'm going to define white, black, blue, and my start and end positions are all in tuples. The graph database that I'm making will look like this, but with 640, let's see, across by 640 down. So all I'm doing is rendering a graph to make a grid. So I'm 640 pixels, or 640 nodes across, 640 nodes down, and also making sure to tie each one of those with an edge. And then deleting out all the white pixels, which are the walls. The black pixels are the paths. So let's see. Okay, so at this point I've got the maze structure. Let's see. I want to make sure I run this.
Can you go back up to your little,
To this one?
the diagram.
This diagram?
Is that one pixel represented there?
No, that's, let's see, this is going to be a 3x3 grid. So I can try re-rendering this thing. This is one of those things where I needed to nail down this position argument as something other than the spring layout, because it'll give me a different render every time. I'd like to have 3 across, let's say by 3 down. But let's see. So now that I've got that set up, this is one of the most missed features in graph databases, is the algorithms. Let's say, there are so many algorithms in Networkx that are already built in. So I'm going to turn this into code and let you see. Let's see, it's got depth first search, it's got breadth first search, it's got A star, which we'll be using. There's the A section, there's the B section, C, chloridal, clicks, communicability, just an intense amount of work. And for each one of those, I want you to know there's huge amounts of documentation about where they pulled that from and let's see, how well it's performant. So let's take a look in, let's see. Oh, I was messing around with the, let's see. This whole thing takes about maybe 15 seconds to run. And so, oh, careful. Spoiler alert, if you want to solve the maze, look away. Here's the path. It was able to do this in about 15 seconds. So we can take a look at the graph properties. So find out how big this path is. It's 194,000 nodes across. Let's say that's the biggest, or the largest connected component in this. This isn't the path. This is the entire maze. There are some pieces of this that are left off because of that number here up in the top corner, but that is a good majority of the maze right there. So let's talk about centrality. Each one of these nodes has a centrality, or you can obtain a centrality score. How central is that particular node in this graph? How they calculate that is they take up all of the paths going from every node. Let's say node 1 to node 10, node 4 to node 9, node 17 to node 7. They will add up all of these paths and find out which one, let's say in this example, node 5 is what you're trying to find the centrality of node 5. How many paths do include node 5 in it? So the centrality score is going to be based off of that percentage. So if we take a look, we can graph the centrality, the betweenness centrality. let's see, in this case, node 5 pops to the top. Let's see, it is the most central. If you took this out, it would disrupt this particular graph quite, let's see, quite well. Let's say there would be 3 sections of this graph. There's other types of centrality measures. There's closeness centrality. How close is this 5 to all of the other nodes? And it doesn't matter how you measure it, node 5 still pops to the top. Okay. How does this tie in with our maze problem? In our maze path, if you could evaluate the centrality, you would find out where you would be wasting time. It shows you it would show you nodes along the path, and it would show you this is where, let's see, nodes that are central have a tendency to, if you made the wrong decision, you would be wasting several days worth of time in this particular instance. So centrality can have good implications, centrality can have bad implications, or let's say, in this case, it's be careful. Let's see, if you are central, if you are in a city that somebody is trying to attack, that is a bad centrality score. Or you would get a high centrality value if you're in New York City or something like that. But it wouldn't be a good thing. So you'd have to interpret it for your domain. All right, so this is a example of concept graph. In this case, what I was doing was taking the SymPy symbols. I was trying to correlate something like E equals MC squared. And if I put that into a graph, because they're all in the same equation, I made a big triangle out of it. What I wanted to find out was, what is the concentration of a physics book? So I went through a physics book, I put in a bunch of the equations, and pulled out their symbols. Here's the equations for the first 8 chapters, and then, let's see, made sure to make a graph of this whole thing. So what I wanted to find out was, how important are these concepts to that first eight chapters? And by, let's see, each one of these equations might be involved in, let's see, or each one of these nodes might be involved in several equations. So let's see, or if you wanted to get from one node to another, let's say like power to the speed of light, these are the things that you would need to take into consideration: velocity and mass. They would either have to be zeroed out in your equation, or you'd have to deal with them somehow. Now, this is not the only path. This is just one of the shortest paths. All right, and it's pretty easy to write these files out. In NX, you can use GraphML files, or if you're going to use Gephi, you can use GEFX or GXF files as outputs. So, well, these are some of the awesome creators or contributors to this. Yes? Let's see. On the graph of physics things, what does the centrality mean? That means it's going to be more central. Let's see. It's probably going to be something you want to study more, focus more time on. Which property was the high centrality score? I'm not. Sorry, I can't hear. I think so. Right. Let's see. Question is, which one of these terms have the highest centrality score? to do this. Let's see. Looks like Mass is the winner. Plot that. All right.
You might need to plot that another time. We've got 2 minutes now.
Oh, 2 minutes. Okay. Any other questions?
Wrap up.
Well, let's see. If there's no other questions, there's a software called Gephi, and it's kind of like the Photoshop of Networkx or of graph database graphs. You can tease out areas out of your graph database and be able to make sense of it just a little bit more. So you can delete entire sections just by using mouse clicks. So wonderful thing to check out. If there's no other questions, well, that's going to be it.